Hey, welcome back to Fat Mama Physics. In this video, we are going to go over an example on the Millikan oil drop experiment and kind of the basics of how it works. So let's essentially describe what's going on here. You have this oil spray that will eject these very tiny oil particles, very light oil particles, into this chamber, in which they will get zapped by some sort of by charged particles, knocking off either electron or two off of these oil particles, off their molecules, so that they'll be charged before they come down into this before they fall into this gap here, which then after they enter this gap, they are subjected to an electric field, a uniform electric field for that matter, and which they will, in a sense, not move. Or you might have to tweak the electric field until it does not move, and which you can use that for, you can do that for all sorts of different applications. Essentially, you could do, if you know exactly if you're knocking off exactly one electron off of these oil particles, then you can probably use this to measure, say, the mass of each oil particle, or vice versa, or for that matter. Although I don't think this question does that. It's doing something a little bit different. So let's see what this question is about. The Millikan oil drop experiment, it electrically charges oil particles of, okay, you're given the mass, okay? So you're given the mass of all of these little oil particles that are entering this chamber. They are placed against, so they're charged. So they're already charged. They're going to enter this electric field. This electric field has a distance of separation of 9.40 centimeters and a potential difference, so delta V here is 8.65 times 10 to the power 4 volts. So the electric potential, because of that, because of this field, the oil particles will stop moving based off the direction of the field. We want to find the charge on these oil particles. So let's think about objects when they are not moving. First of all, if they're in an electric field and they're charged, they must experience an electrostatic force. So that's one force acting on this charged particle. We don't know in which direction. But since they are not moving, there must be two equal and opposite forces acting on these oil particles. We know that since they are falling, they must be subjected to a force due to gravity, and in which the opposite force acting on them has to be the electrostatic field. Electrostatic force. If it weren't for electrostatic force, these oil particles will just keep falling and, of course, move, accelerate, in fact. So we know that based off of this, what we're told, these two forces are equal. We also know Fg is equal to the mass times gravity, in which the mass is given in here for the oil particles. The electrostatic force acting on a particle, we know is based off of the electric field times the charge. That's from the basic definition of the electric field, is the force per unit of charge acting on a test charge. So if we substitute this over here, along with the gravitational field, I'm just losing function here. With the gravitational force acting on the two, then we get EQ is equal to the mass of the object times gravity. But we don't have the electric field. We have to get the electric field another way. And to do that, we probably need to use the idea of a uniform electric field across two parallel plates as it's over here, delta V over the distance of separation of these two plates. So after we do, you know what, I'm just going to substitute this in here, okay? Let's just do a substitution. I just want to grab my calculator. That's my fault. So here we have delta V over D. This was the electric field times the charge on your particle equals to the mass of the oil particles times gravity. So we want to solve for the Q, or we want to solve for the charge. So I'm just going to I'm going to multiply D up and then divide both sides by V, or I just do a cross multiply if that makes more sense mathematically for you. So these go away and I'm left with the charge is equal to mg times d separation over delta v, which I'm just going to start putting things in. 1.5 times 10 to the power negative 14. Gravity 9.81. Sorry, no space for units here. D separation, don't forget, got to convert this into meters. This is 0.094. And then all of that divided by the voltage, or the potential difference of 8.65 times 10 to the power of 4 volts. I have space for those over there, okay? Very messy, I know. So let's put it in. Oops. And here I get 1.599 times 10 to the power of negative 19. Let's do a rounding here. So about 3 sig figs, we get 9 round this 9's up to a 0, which rounds up to 1.60 times 10 to the power of negative 19 coulombs. And notice it interesting there, that is the elementary charge of, so essentially what this is saying that is that these oil particles are either deficient by an electron or have an excess of an electron compared to the number of protons that they have. So either they gained or lost an electron. Probably lost because they get knocked out, but alas, here it is, Millikan ore drop. So again, Newton's we look at Newton's second law again, so looking at the balance of forces and using that to figure out the charge. So very powerful tool. Anyways, I hope you learned something from this video. Thank you for watching. Fat Mama Physics signing out.